You are so close to done. Right. So this is our last little piece to think about, and then it is almost time for you to enjoy the sunshine of the summer. We have done energy, we've done momentum, we've done rotational momentum, translational energy, conservation of momentum mixed with energy. The only piece we have left is to think in terms of rotational energy. So if you remember, I have, let's see, translational kinetic energy. So KE translational, that was 1/2 mv squared. So rotational, remember our kind of segue between the two pieces was to say that for something rotational, mass is I, velocity is just omega, so omega squared. So KE rotational then is 1/2 I omega squared. So it's not too bad. It's just kind of an adaptation of things that we've already been using. So this question then gives us that the weight of a merry-go-round is 800 newtons. It has this radius of 1.5 meters. I'm going to apply a 50 Newton force tangentially to it, and I want to know what the kinetic energy is at 3 seconds. So this kind of starts bringing everything back together, doesn't it? So let's see. I know a weight of this thing. I'm applying a force to it. So here's my merry-go-round, and remember, tangentially would be like pushing it like that away. So here is the radius. So this would be a torque applied at 90 degrees. So I have then my torque, if I remind myself, is going to be the force times the distance from the axis of rotation times sine of theta. So the angle between this and this. So this is 90, so that's just 1. And my torque then is going to be, let's see, 50 newtons times this 1.5 meters. Okay, so I have that, but I feel like that's not really getting me to where I need to be. So what do we know when I have a net force, or a net torque in this case, applied to something? Doesn't that mean that I have acceleration? So do you recall that we can go then, like if I have the sum of torques, or the sum of my net torques is going to equal, let's see, something like I alpha? Because remember, I'm rotating, so this is instead of my mass, and alpha is for my rate of acceleration going in a circle. So I can look at this and be like, okay, so I have 50 newtons. I know this. I know my net torque. If I get alpha, won't that give me the rate of acceleration? If I'm starting from rest and I know how long I'm doing it, can't I convert that into then an omega? So let's see. The one thing I need is an I. And the merry-go-round, the one thing we know about that is that it has this 1/2 mr squared. 1/2 mr squared. And you can look this up in your book. Again, I think it's page 220. This is just a disk. So a disk with a evenly distributed mass about its center. So I know this. I can rewrite this then as 50 newtons times my 1.5 meters divided by 1/2 m. I have 800 newtons as the weight. So I know that the force of gravity equals mg, and this piece here is the weight, right? So if I have that, if I divide by g, that will give me, so I'll have 800 newtons then divided by 9.8 meters per second squared. And that ends up giving me my weight of what? Give me a second. Oh, there we go. 81.63 kilograms. So 1/2 mr squared, 81.63 times r squared, my 1.5 squared. So there's one nice thing here. I see one piece that cancels out. See, this 1.5 is going to cancel out with that. So the only thing I'm going to do, I can rewrite this if I want. I'm going to end up with 2 times 50. That's just that 1/2 popping up top because it's a fraction. So the 2 is going to come up top, divided by 81.63 times 1.5. Let's see what that gives me. Okay, so I have 0.817 radians per second squared, and it wanted the kinetic energy. So the last thing I need to do is remind myself that this thing I just solved for is alpha. So let's see, how can we get there? Well, I feel like the most straightforward equation that comes to mind is to say something like this: omega final is going to be what? It's this initial omega, it's initial rotation rate, plus AT. Let's think about this. This would be omega final minus an omega initial if I divide or move one to the other side. If I divide by time, well, a change in omega over time, well, that is my alpha. That is acceleration, right? So that is a good option, and I know I'm starting from rest. So my omega final then is going to be my alpha, this 0.817 times time, times this 3 seconds. What does that give me? So times 3, so my omega final is 2.45 radians per second. Radians per second. Cool. So I'm down to just putting values in then. I have that my rotational energy is this 1/2 I omega squared. We've already determined what the mass is. So 1/2, there's the mass, radius squared is given. So there's my I part. And my kinetic energy is another 1/2. So the most common mistake made here is when you write this out is to forget that this 1/2 does live there. That is the inertia. And kinetic energy rotational is still this 1/2 factor. So you actually have 1/4 here when I'm dealing with a disk. Don't forget these coefficients change depending on the shape of the thing that's rotating. But in this case, this will indeed be 1/4. And then mass, radius squared, omega squared, well, we just figured that out. So it is now just putting all these things into, let's move this over. So my KE rotational then is my 1/2 times 1/2, so 1/4 mass R squared omega squared. There we go. So that's simplified down nicely. Now let's put in some values. So 1/4 times the mass of this thing, this 81.63, times R squared, 1.5 squared, forgot the 1, times omega squared, times 2.45, 2.4. Oh, I'm running out of space. Okay, so let's see what we get. We get that squared times 1.5 squared times 81.63, 63. All of that divided by 4 gives me a kinetic energy of 276 joules. There we go. So not too bad. This, again, is just bringing everything together. That's what we've been gearing up towards, is kind of adding piece by piece by piece. And now we're going to bring all those pieces together and have them relate to one another. So the biggest things that I can say to you to kind of help you keep that framework together is that first look to see, what pieces of information are you given? What have you been asked for? Like this one is asking me for my kinetic energy. So go ahead and write that out, right? And then look and be like, okay, do I know its inertia? Well, it gave me its weight, so I can get to its mass, so I can get to its inertia, no problem. Do I know omega? No, I don't. Okay, so what information have I been given? Well, there's a force that's been applied and an amount of time that force has been applied. So if I know that, then that tells me I can get to acceleration or alpha. If I have that and I know the amount of time, then I can get to omega, so I can get there. I can start pulling all these things together. You got it.